diffraction. This is the another phenomena to prove that light has wave nature. One of the phenomena is interference, another phenomena diffraction. This is the second topic in wave optics in our syllabus first unit. Okay, diffraction. Diffraction is the phenomena of bending of light around the corner of obstacle and spreading of light wave into geometrical shadow region of obstacle placed in a path of light is called diffraction. Diffraction means when the light where you put an obstacle in the propagation of light wave. This is an obstacle. This is the light wave propagation. When you put an obstacle in the propagation of the light wave, that light bend at the corners of the obstacle and form an intensity on that geometrical shadow. This is called the diffraction. Totally, diffraction means bending nature of the light wave when you put an obstacle. And the condition for diffraction is the size of an obstacle is comparable with the wavelength of the source. Okay, the size of the obstacle is comparable with the must be comparable with the wavelength of the source. Diffraction phenomena is divided into two types: fresnel diffraction, Fraunhofer diffraction. Fresnel diffraction, Fraunhofer diffraction. We have two types of diffractions. In our syllabus, we take only Fraunhofer diffraction. Okay, in Fraunhofer diffraction, we take single slit. General example of diffraction is general example of diffraction in our nature is this picture. Here clouds take as the obstacle. Sunlight when obstacle placed here, that light bend at the edges of the obstacle and form intensity in the geometrical in the shadow. Here we take the very important question, Fraunhofer diffraction due to single slit. Suppose we take a single slit. Single slit means here this is the slit, only the light propagated through this A and B. Okay. So here we take plane wavefront. We take plane wavefront and Fraunhofer diffraction means here we take plane wavefront and this lenses used here. Okay, lenses are used and take plane wavefront. So here we take plane wavefront. That wavefront incident on this slit. Okay, incident on it. The diffraction light through this slit is focused by means of a convex lens. This is a light focused by means of a convex lens on this screen. According to Huygens theory, every point on the wavefront in the plane of slit is a source of secondary wavelets. Every point on the wavefront is the source of the secondary wavelets. These are which is spread out the light in all directions. Which is spread in light in all directions. These wavelets traveling normal to the slit that is focused at the point P1. So the P naught is the bright center image. The secondary wavelets traveling at angle theta with normal. The secondary wavelets traveling at angle theta with the normal are focused at point P1 on the screen depending on the path difference. The point P1 may have maximum minimum intensity. See here, the secondary wavelets making an angle theta. These are the secondary wavelets. These are the primary wavelets. These primary wavelets concentrated at the point P0 are focused at point P0 with the lens, and the secondary wavelets are focused at the point P1. This is the bright intensity, brightness, maximum brightness occur. So this is called the principal maximum, central maximum, and here P1 the intensity either maximum or minimum. So we find here maximum intensity or minimum intensity. To find the point intensity of the P1, to find the intensity of the P1, let us draw the normal C from A, the light ray at B. See here, we draw normal from A to C on that light ray B. Okay. For part difference, we find here. We draw a normal. The part difference between the wavelets from A and B in the direction theta is given by part difference is equal to BC is equal to AB sin theta. The part difference is equal to BC is equal to part difference BC is equal to AB sin theta. BC is equal to, here AB is the width of the slit, E sin theta. Phase difference is equal to, actually the relation between phase difference and part difference is equal to 2 pi by lambda. Phase difference is equal to 2 pi by lambda path difference. So 2 pi by phase difference is equal to 2 pi by lambda part difference. 2 pi by lambda, here part difference is E sin theta. So phase difference is equal to 2 pi by lambda E sin theta. Let the width of the slits here, see here, let the width of the slit is split into n slits. The width of the E slit into n slits. Phase difference is equal to 2 pi by lambda path difference. This is phase difference is equal to 2 pi by lambda path difference. That is equal to 2 pi by lambda E sin theta. Let the width of the slit be divided into n equal parts. The amplitude of the wave from each slit is A. The phase difference between any two successive waves is 1 by n, because we take the slit as n slits. Total phase difference is equal to 1 by n. Here phase difference is 2 pi by lambda E sin theta. So 2 pi by E sin theta by lambda. We assume this is a D. Okay, this is a D. Using the method of vector addition of amplitude, we find the resultant amplitude R. Using vector addition here, R is equal to the resultant amplitude R is equal to A sin nd by 2 by sin d by 2. Here D is the, this is the D. Here D is this. Okay. So R is equal to, you substitute in place of D, 2 pi E sin theta by n lambda. This is the D value. Cancel terms. Here we put pi E sin theta by lambda as alpha. We take that value as alpha. Pi E sin theta by lambda is equal to alpha. So resultant amplitude R is equal to A sin alpha by alpha n. Alpha, here we take alpha by n is small, so we take sin alpha by n as alpha by n, and Na sin alpha by alpha. R is equal to A sin alpha by alpha. R is equal to A sin alpha by alpha. Here in place of Na we take capital A, because A is the amplitude of light wave in each slit. Here we have n slits, so n into A is the total amplitude, that is equal to A sin alpha by alpha. Intensity, this is the resultant amplitude, and intensity is the square of the amplitude, so I is equal to R square, A square sin alpha square, sin square alpha by alpha square. We find the principal maxima. Okay, first we find the principal maxima. At the center we obtain the, at the point of P naught we obtain the principal maxima. We find the condition for that principal maxima. The resultant amplitude can be written as this resultant amplitude. So this is the resultant amplitude, R is equal to A sin alpha by alpha. We write this in another form, A by alpha and sin alpha. Sin alpha expand the sin alpha, that is alpha minus alpha cube by 3 cube plus alpha 5 by 5 factorial, sorry, minus alpha power 7 by 7 factorial, and so on. So we common the alpha and get alpha cancel. Here we take alpha, A by alpha get cancel. A into 1 minus alpha square by 3 factorial plus alpha 4 by 5 factorial minus alpha 6 or 6 by 7 factorial. I will be maximum when the value of R is maximum. Intensity maximum, I means intensity maximum when amplitude is maximum. For this value, the negative term must be vanished, that is alpha is equal to 0. So phi E sin theta by lambda is equal to 0. Here we put in this equation we put alpha is equal to 0. Alpha is equal to 0. We obtain maximum amplitude. By maximum amplitude, we obtain maximum amplitude. We obtain maximum intensity. So alpha is equal to 0. Pi e sin theta by lambda is equal to 0. Then sin theta is equal to 0. Sin theta is equal to 0. Theta is equal to 0. So theta is equal to 0 is the condition for maximum intensity in that central maximum. Minimum intensity positions. Minimum intensity. Intensity will be minimum when sin alpha is equal to 0. Sin alpha is equal to 0, then intensity becomes minimum. Alpha is equal to plus or minus m lambda. When sin 0, either plus or minus m lambda. Alpha is equal to plus or minus m lambda. Pi e sin theta by lambda is equal to plus or minus m lambda. Pi e, because alpha is equal to pi e sin theta by lambda. So pi e sin theta by lambda is equal to plus or minus m lambda. Then e sin theta is equal to plus or minus m lambda. This is the condition for minimum intensity. Condition for maximum intensity is theta is equal to 0 degrees, and the condition for minimum intensity is e sin theta is equal to plus or minus m lambda. So we obtain the point of minimum intensity on either side of the principal maximum. Either side of the principal maximum. Secondary maximum. In between these minima we get secondary maxima. In two minimas we get secondary maxima. These positions can be obtained by differentiating the expression of I with respect to differentiating with I with respect to alpha and equating to 0. Here we differentiating with respect to alpha and equating to 0. Here I is a square sin alpha by alpha square. Differentiating, we obtain alpha is equal to tan alpha. Here we differentiating a square is constant. Sin square differentiate 2 sin alpha, and sin alpha sin square. Here you take u by v formula. V u by v formula. Sin alpha by alpha square. 2 sin alpha by alpha. Then sin alpha by alpha is u by v. Alpha cos alpha minus sin alpha by alpha square is equal to 0. Then we obtain alpha is equal to tan alpha. Here the equation alpha is equal to tan alpha, we take as a graph. Tan alpha is one graph and y is equal to tan alpha, y is equal to alpha. We draw those two graphs. Those two graphs intersection points are the secondary maximum points. So y is equal to alpha and y is equal to tan alpha. These graphs are y is equal to tan alpha. So see here, y is equal to tan alpha, and this is the y is equal to alpha. So these two graphs intersection points are given the maximum intensity points. So alpha is equal to 0, one principal maximum, alpha is equal to plus or minus 3 by 2, secondary maximum, alpha is equal to plus or minus 5 by 2 is the second order secondary maximum. So this is the intensity distribution curve. That means this is the central maximum, this is the principal maximum, central maximum, this is the minimum, either side of the maximum, these are minima points, these are the secondary maximum points and minimum, and this is the secondary maximum. So this is the first order secondary maximum, this is the second order secondary maximum. So either side we obtain the secondary maximum to the principal maximum. This is the intensity distribution curve to the single side. Okay. Next we go to Fraunhofer diffraction at a double slit. Fraunhofer diffraction at a double slit. In the previous question we did single slit, that means single two one monochromatic light wavelength lambda is incident on the two slits. The light diffracted from these two slits and focused by the lens on the screen. The diffraction at two slits is the combination of the diffraction as well as interference. See here, light waves, monochromatic light waves passes through these two slits and diffraction takes place in these two slits. Here, each slit like a single slit. This is a one single slit. This is another single slit. Okay. These two diffracted rays through the single slits, that means S1 and S2. Again, interference takes place. Those two diffracted rays again takes place. The intensity, additional intensity comes from these two slits. Okay. And here, diffraction as well as interference takes place. The wavelets traveling in a direction of the incident light come to the focus at P0. By the wavelets traveling in the direction making an angle theta comes to the P1. See here. So now comes wavelets, primary wavelets at P0, secondary wavelets at P1. So here two slits is a two single slits. Okay. Resultant amplitude through single slit is A sin alpha by alpha. Each slit resultant amplitude is A sin alpha by alpha, where alpha is equal to pi e sin theta by lambda. We use a double slit. From each slit we get wavelet of the amplitude A sin alpha in a direction. To calculate the path difference between the wavelets, let us draw a normal S1 S1k to the wave. For path difference, we draw a normal from S1 to K on S2. Okay. Path difference is equal to S2K, that is equal to E plus D sin theta. Path difference is equal to S2K, that is equal to E plus D sin theta. Phase difference. You know already phase difference is equal to 2 pi by lambda E plus D sin theta. To find the resultant amplitude at P1, we use vector method from figure. See here, in this figure, vector method, this is the one vector, this is the another vector. This vector is resultant amplitude through S1 slit, A sin alpha by alpha. This vector is resultant amplitude to S2 slit, A sin alpha by alpha. So, resultant amplitude, resultant vector, you know already resultant vector, OH square is equal to OG square plus GH square plus OG into GH into cos delta. Okay, this is the resultant vector formula. Here OH square is R square, resultant amplitude, and OG square is A sin alpha by alpha square, GH also A sin alpha by alpha square, plus 2 into A sin alpha by alpha, A sin alpha by alpha cos delta. So we substitute all these values from previous triangle, previous vectors. R square is equal to A square, sin alpha by alpha square. Obtain this. So 2 plus 2 cos delta. 1 plus cos delta is equal to 2 cos square delta by 2. This is the formula. In this place we substitute this formula, 2 cos square delta by 2 by 2. 2 to get cancelled. Finally R square is equal to 4A square sin alpha by alpha square cos square. We substitute delta value pi into E plus D sin theta by lambda here. Here we take this is as beta, pi into E plus D sin theta by lambda as beta. So the equation is R square 4A square sin alpha by alpha square cos square beta. See this resultant amplitude, that is the intensity, resultant intensity R square, I is equal to R square, that is 4A square sin alpha by alpha square cos square beta. This resultant amplitude, resultant intensity due to diffraction. See this single slit resultant amplitude, resultant intensity A square sin alpha by alpha square. But additional word this in this here cos square beta. This intensity due to again the diffracted clear that the A square sin alpha by alpha square is due to diffraction, cos square beta is due to interference. For diffraction, already we know in single state, the principal maxima condition is beta is equal to 0 and minima condition. Here see this diagram, intensity distribution curve. This is the principal maxima. When diffraction takes place through the single slit, the intensity changes like this: principal maxima, secondary maxima, minima. The condition for principal maxima is theta is equal to 0 and the condition for minima is alpha is equal to plus or minus E sin theta is equal to plus or minus m lambda, and here the secondary maxima's points are alpha is equal to plus or minus 3 by 2 and plus or minus 5 by 2 and so on. This is the diffraction effect. In the single double slit, diffraction takes place and interference takes place. Here, intensity distribution due to the diffraction is this one, maxima intensity. This is intensity distributed due to the diffraction. The intensity distributed like this. And we go to interference. Interference effect. The interference term cos square beta. Maximum interference means either maxima or minima. Both having the same intensities. Having we go to increase the order, the intensity is same width. Maximas all maximas have the same width, minimas have same width. So, but in a diffraction pattern, in see here in the diffraction pattern, see this diffraction pattern, the intensity of the maxima when order increases, the intensity decreases. Order increases, the intensity decreases. But in interference, the intensity same for all maxima maximas. So here maxima will occur cos square beta is equal to 1. Beta is equal to plus or minus n pi. Pi into here pi into e plus d sin theta by lambda is equal to plus or minus n. Because beta is in previous we take beta as b pi into e plus d sin theta by lambda. So in place of beta we substitute that is equal to plus or minus n pi. Pi get cancelled because cos is maximum at pi n pi. So e plus d sin theta is equal to plus or minus n lambda. Pi get cancelled. Minimum will occur for cos square beta is equal to 0. Beta is equal to plus or minus 2n plus 1 pi by 2. And e plus d sin theta is equal to, we substitute beta value, beta pi into e plus d sin theta is equal to, so pi into e plus d sin theta by lambda is equal to n plus or minus 1 pi by 2. Pi get cancelled. E plus d sin theta is equal to plus or minus 2n plus 1 lambda by 2. So intensity distribution. So in this interference, intensity distributed like this. And finally, the resultant distribution, intensity distribution. See here, this is diffraction. This is intensity distribution in due to the diffraction. This is the intensity distribution due to diffraction. Okay. Here the intensity again the intensity distributed due to interference. This pattern due to diffraction. This pattern due to interference. Finally, the intensity distributed like this in the second double slit. Okay, in double slit the intensity distributed like this. Okay, so that is the double slit Fraunhofer diffraction due to double slit. Very important question. In that, you see this resultant distribution curve. At the minimum also there exists a intensity. Okay. So this is the intensity distribution curve double slit. Okay. Next we go to difference between Fresnel diffraction and Fraunhofer diffraction. Fresnel diffraction and Fraunhofer diffraction. We have two types of diffractions, Fresnel and Fraunhofer diffraction. In Fresnel diffraction, the light source and screen are finite distance from the obstacle. From obstacle, the source and screen at finite distance, but in Fraunhofer diffraction, those are infinite distance. The wavefront undergoing diffraction is either spherical or cylindrical. In Fresnel diffraction, we take the spherical or cylindrical wavefronts, but in Fraunhofer diffraction, we take only plane wavefront. Lenses are not used in Fresnel diffraction, but in Fraunhofer diffraction, we use the lenses. Next, which is the critical to, it is complicated to study. Frontal diffraction is complicated to study, but Fraunhofer diffraction is easy to study. Either a point source or an illuminated narrow slit is used, extended source and finite distance is used. Okay, these are the differences between Fresnel diffraction and Fraunhofer diffraction. Next difference is interference and diffraction. Interference takes place two wavelets superimposed, but diffraction takes place two secondary wavelets are originated from different parts of the same wavelength. Okay, secondary wavelets takes place here. The primary wavelets interference we take primary wavelets. The fringes normally have equal widths. The width of the width between fringes is never equal. Here in interference we obtain equal width of the fringes, but in diffraction the fringe width changes from or increase the order. All the bright fringes have the same intensity. The intensity of bright fringes usually decreases with increase the order. All the dark fringes have zero intensity. The intensity of the dark fringes is not zero. These are the main important differences between interference and diffraction. This is very important question, and also diffraction and Fraunhofer diffraction is also another important question. Okay. Next, last topic in our diffraction grating. Last topic in diffraction grating. An arrangement which consists of large number of parallel slits, sides or slides of the same width and separated by equal opaque spaces is known as diffraction grating. See here, parallel slits. In previous session we know single slit, double slit. Here number of slits. Two parallel lines. In between two parallel lines, one slit. So here number of slits is there. When light incident on this grating, diffraction takes place. So this is called the diffraction grating. Generally we see this diffraction grating in laboratories. Using diffraction grating, we see the diffraction of that light. Using grating, we see the diffraction uh, in our laboratories. Okay, diffraction grating means number of parallel lines separated by equal opaque spaces. Okay, these lines